Welcome back. In this section, we'll be looking at rational expressions, which essentially are like fractions, except instead of just being a number on top of a number, it might be a polynomial on top of a polynomial. But of course, it's still going to have the same sorts of properties that we had for fractions, and the same sort of idea that we had for arithmetic with fractions will apply here too for arithmetic with rational expressions. So first off, if we were talking about fractions that are just number on top of a number, that fraction would be in simplest terms if there was nothing that went into the top and also the bottom, so if there was nothing that could be canceled out. And the same thing is true for rational expressions. Those are in simplest terms if the numerator and the denominator have nothing in common, if there's nothing that can be canceled out. Of course, if we're doing canceling, that means we're going to start off by doing factoring. Because remember that when we're canceling fractions and we're canceling something out of the top and the bottom, what we're canceling is a common factor. So if somebody were to hand me something like x squared minus 4 over x plus 2, I wouldn't be able to start canceling right away until I factor out that numerator. As it currently stands, a lot of people might be thinking about trying to cancel the 2 and the 4, or they might think to try to cancel the x squared and the x, but both of those would be illegal cancelings. We cannot do those. We can only cancel factors, not individual terms. So that means if you wanted to factor it out first, that would be the first move to make, and then you could think about canceling out any factors that you have in common. And we're also going to see that when it comes time to doing arithmetic with rational expressions, everything is much easier if our numerator and our denominator are already factored. So generally, our first move is always going to be to factor as much as we can, then do stuff with it. So here I've got a rational expression, and I'd like to write it in simplest terms. So I need to factor the numerator, and I need to factor the denominator first. The denominator is a nice little difference of squares. X squared is a perfect square, as is 16. So x minus 4, x plus 4 is how I'll factor the bottom. And for the top, I need numbers that multiply to 20 and add up to -9. And that looks like -4 and -5 to me. So x minus 4, x minus 5. And I can see now that I've got a factor in common. There's x minus 4 that's a factor in the top and also in the bottom. So those can be canceled, leaving me with just x minus 5 for the numerator and x plus 4 for the denominator. So when I said as before that it's really a lot of the same properties that we had for fractions, it really is exactly the same properties that we had for fractions where it's number on top of number as we do for rational expressions where it's polynomial on top of polynomial. So for example, if you were asked to multiply two fractions, you would multiply the numerators together and you would multiply the denominators together. And that's exactly what we do with rational expressions as well. Or if you had one fraction divided by another, you would flip and multiply the denominator, and we'd do the same thing with rational expressions. Or if you were adding up two fractions, you'd need to make the same denominator first, then add the tops or subtract the tops, depending on whether you were adding or subtracting. So really, there's nothing surprisingly new here. It's going to involve a little bit of factoring first. So let's just do some examples. Of course, before we do that, a reminder about finding ourselves common denominators. As always with everything in this section, it's easiest if you have your denominator factored first. So if somebody were to hand me these two expressions and say, please add them and then simplify, before I can add those two rational expressions, I'd need to make common denominators. And if I did my factoring first, I'd realize that the denominators already have something in common. When I factor out the two denominators, one of them is x minus 2x plus 2, and the other one is x minus 2x minus 3. So really, they already have x minus 2's in common. One of them has an x plus 2 that the other one doesn't. One of them has an x minus 3 that the other one doesn't. So if we were making common denominators, I would need to have it as x minus 2, x plus 2, x minus 3. I would multiply the first fraction, top and bottom, by x minus 3. I'd multiply the second fraction, top and bottom, by x plus 2, and then I'd be able to add my two rational expressions together. Of course, the making a common denominator, that's only required if we're adding or subtracting, not if we're multiplying or dividing. That's the good news. So now let's do an example where we have to make common denominators. This one, I've got subtraction as well as addition. I've got one rational expression minus another one plus a third one. So let's get ourselves started out by factoring. Our first denominator, multiplying to 3 and adding up to -4, that's -3 and -1, so x minus 3, x minus 1. The second one, multiplying to 6 and adding up to -5, that's x minus 2, x minus 3. And our last denominator is already as simplified as it's going to get. X minus 3 is not going to factor any further. So if we're looking at what we currently have, all three of our denominators have an x minus 3 in them already. One of them has an x minus 1 and the other ones don't. One of them has an x minus 2 and the other ones don't. So if I'm making my common denominators, I guess for the first one, I'll multiply top and bottom by x minus 2 to put in the thing that it's missing. For the second one, I'll put top and bottom, put in an x minus 1 to put in the thing that it's missing. And for the third one, it'll need to have both the x minus 1 and the x minus 2. So now I've got three rational expressions. They all have x minus 1, x minus 2, x minus 3 in their denominators. So I can make one big rational expression now with that common denominator of x minus 1, x minus 2, x minus 3. And I'll just take my first numerator, my second numerator, and my third numerator, and put them all together. So now the only thing left for me to do is just to simplify that numerator and then factor it if I can factor it, and hopefully that'll be that. As far as the denominator goes, I'm not going to do anything with that. We're going to leave our answers in factored form, so if you're thinking about multiplying out the denominator, resist that urge. That's the opposite of what we want to do. The denominator is already as nice as it's going to get. We're not going to do any factoring because that'll just make things worse. Okay, so let's begin. We have the 1 times x minus 2, that's just x minus 2. We have a minus x times x plus 1. So when I multiply that together, I'll have a minus x times x, a negative x squared. I'll have a minus x times 1, that's a plus an x. And then for the last term that we've got there, that's a 1 times an x minus 1 times an x minus 2. So if we multiply that out, we'll have x times x, which is x squared, x times negative 2, negative 1 times x, negative 1 times negative 2. There we go. That's all of our numerator, all over x minus 1, x minus 2, x minus 3. And now if we're just cleaning this up a little bit further, there's some things that are going to cancel out for us. We have the minus x squared and the plus x squared. Those are gone. So it looks like there's no x squareds in our numerator. As far as x's go, we have 1x plus another x minus 2x minus another x. So if we combine all of our x's together, there's negative 1x. And if we combine all of our constants together, those cancel each other out. There's a minus 2 and a plus 2. So it looks like my numerator is just negative x. and my denominator, x minus 1, x minus 2, x minus 3. All right, let's just do another example here. So we've done some addition and subtraction. Let's do some multiplication. Again, this is something that's going to be easiest done if we've already factored. If we don't factor, then that means you would have to take x squared and multiply it by everybody, then 5x and multiply it by everybody, then 6 and multiply it by everybody, and then try to factor afterwards, which sounds like a terrible plan. The better plan is to factor in advance, and then maybe we won't have to do any extra work after that, maybe just a little bit of canceling. So let's start off. We have for the first little rational expression, numbers that multiply to 6 and add to -5. That's -2 and -3. So x minus 2, x minus 3. And our denominator is a difference of squares, x minus 4, x plus 4. And in our second fraction, we've got multiplying to 4 and adding to -5. That's x minus 1, x minus 4. And in the denominator, we have multiplying to -2 and adding up to -1. We have x minus 2, x plus 1. So really what we're going to have when we multiply these together, remember multiplying fractions involves multiplying the numerators together and multiplying the denominators together. So we would have in the numerator x minus 2, x minus 3, x minus 1, x minus 4. And in our denominator we'd have x minus 4, x plus 4, x minus 2, x plus 1. Now, of course, there are some things that can cancel. Anytime we're multiplying two or more fractions together, if there's something in one of the numerators that cancels with something in one of the denominators, then we can cancel it out before we multiply. So I notice we've got an x minus 2 in the top and also the bottom. Those will cancel. We have an x minus 4 in the top and also the bottom, so those will cancel. So what'll I be left with? Just x minus 3, x minus 1 for the numerator, and in the denominator, x plus 4, x plus 1. And again, we're leaving our answer in factored form, so you might be feeling a desire to start multiplying everybody out. Resist that urge. That's as far as we need to go, and we're going to leave our answer in that factored form.